Visions, trying to make sense of a now, trying to make sense of a past, to show us how. Visions, imagining the worlds that could be, shaping a mosaic of fate for all sentient beings. Visions, cycles of growth and decay, cascading chains of events. Visions, avoidable suffering and pain. We are patiently itching away toward unreachable utopias. Visions, enslaved by the forces of nature, elevated by mindless replicators, challenge to steer our collective destiny. Visions, look at the magic of reality, while accepting with honesty that we can't know for sure what's next. No, we can't know. We are here together. We are here together.
Cool, it's working. Let me just check the voice. Okay, that's fine. Okay, this fan is very squeaky. That's all right. So yep. So I came back nicer on 7th of June, right? 7th of June, and yeah, I've been studying things from topology, and I reached 3 tangent bundles. Okay, let me just list them out, what I've read. So I've started with, this is from whatever I've covered here in these dates I will review today, and yeah. So the first topic was topology. We have seen the definitions of it, we have seen some examples of it, we have we have seen product topology, induced topology, metric topology, standard topology on real lines. Then we've introduced the notions of continuity and convergence in the topological space. How do you see them? We've defined those. And then the interesting thing, which was a topological proof for infinitude of primes. So that was an interesting thing. Infinitude of primes. And then we started looking at topological properties. We continued topology, and in the second part of the first part of the second lecture, we have seen topological properties, namely the separation axioms. Anyway, we have seen T1, T2 or Hausdorff spaces, and then we have seen, importantly, some invariant with compactness, paracompactness, paracompactness, and we have seen an interesting theorem in an Hausdorff topological space that if it is paracompact if and only if it's every open cover amidst a partition of unity subordinate to that cover. And I've seen a theorem somewhere that there is some theorem on metrizable spaces that if it is metrizable if and only if something related to paracompactness, and I will probe this thing also. It looks interesting. Okay. Then connectedness, path connectedness. Now I have just skipped some things hopefully it won't crash again, but yeah, connectedness, path connectedness, and path connected, and then look, we come to homotopic curves in the fundamental group. Homotopic curves, the notion of a space. On a space you define it's interesting. It's if you just consider a space, and you can just see what curves you can draw, what continuous curves you can draw, which can be smoothly deformed to each other. Now I'm using some shady terms, but they all will be clarified in due discussions. But yeah, on a space you define these curves. You have these curves, and you define a homotopic. You define we define space as a homotopy if there exists a continuous map from that can. There are details, but yeah, which essentially says that you can deform all these curves smoothly from one curve to another. And now, why do you consider 2 points? Just consider 1 point and loop back around it. I guess that's, I don't know what helps, what exactly changes here, and how helpful is it, but I kind of see it. We'll discuss about it. But if you take a loop, and then you take the you then you define the loop space. Okay, all the continuous curves that are these, okay, all continuous curves, we take them and and why did we define a concatenation? Okay, we define a concatenation so that you can take two loops and produce another thing. You can run through two loops, something like that. Then the fundamental group of a topological space is the set. The loop space modulo homotopy. Exactly. If you look through the classes of homotopy, your loop space looks in a certain way. That's the fundamental group for you. Ignore everything that could be continuously deformed. Right? Look through the homotopy and then so how do you get two distinct sets, two distinct balanced classes if you wish in a loop space? It is again fundamental group is at a point P. You have a fixed point, you loop through it, you come back to it. Fundamental group of simple S2 is just one. It's just one identity. Okay. Cylinder somehow. I'll take a course in future, but yeah. So the next thing is we'll focus on topological manifolds. And manifold bundles. Okay. Yeah, in recent lecture he even started using set bundles. So now I appreciate the word manifold bundles. And topological manifolds, we're discussing topology, not discussing any other structures. But yeah, what did you do in this? What did we study here? Of course, we define what a manifold is. A paracompact Hausdorff topological space. It's called a d-dimensional manifold. For all points in manifold, there exists an open set. Again, the subtlety here is you define an open set in our topology. You provide a set of open sets which defines the topology of on M. And homeomorphism X from that open set to some subset of RD. Yeah, locally Euclidean. A paracompact Hausdorff topological space is called d-dimensional manifold if it is locally Euclidean. But the precise definition is for all P in M, this is an open set and that is homeomorphic to a subset of RD. Cool. So yeah, looking through the topological glasses now, you can identify all homeomorphic manifolds. S2 circle of S2 is S2 subset of R3 is topologically homomorphic to S1 in R2 squared in R2 in a loop which doesn't cross itself in R3. Doesn't cross itself means it's embedded in R3. It's essentially a S1 as subset of R3, and you can just go on. And real number is Okay. Started constructing new manifolds out of old manifolds. For example, submanifolds, product manifolds, and then we define bundles. Yeah, connected, right? The product manifolds and submanifolds and bundles. So bundles, you see them as this triple with a total space with a projection map from the base space M to E and the base space M. This is the triple, right? E, pi, and M. Total space, projection map from M to E and M. Yeah, where M and E are manifolds, logical manifolds. Product bundle, or it's never called a bundle. And, yeah, there is some subtlety there which we call the product manifold, M cross E. You kind of generalize the notion of product, taking products via bundles, right? Yours is not a product. A product is a product. Bundle is a bundle, but you can have a different bundle. You can combine spaces in different ways. Here it is given by pi, projection map, and turns out they're useful in many ways, which we'll get into next weeks. Okay. Then we went on to define a fiber bundle, having a same fiber up to isomorphisms, topological isomorphisms, at every point in manifold. Then we saw good example of that. We saw a section. What a section is. He gave a very interesting example of wave function as a section of C-line bundle over the physical manifold, whatever that is. So, what did he? Bundles, importantly bundles. In that we have discussed fiber bundles, fiber bundle section. And then we'll continue discussing about bundles. We define sub-bundles. We define bundle morphisms. Bundle morphisms. Then bundle isomorphisms and isomorphic bundles and bundle morphisms, isomorphism, the notion of isomorphism in bundle theory, and then locally isomorphic, and then some terminology which is some trivial bundle, locally trivial bundle. Locally trivial bundles, and we define so-called locally any section can be represented as a map from base space to fiber. A section as a local function. Just map. Just locally it's a map from that to that. Okay. That subtlety, whatever that is, I don't see it. Of course it's a map. Is it a function? That's the problem I was having. Is it a function locally? Map, of course it is a map locally. Let's see that, right? Let's see section as a local map, locally any section as a map from base space to fiber. That, base space to fiber. Acha. Actually, this notion was resulted in a very specific case of product bundles where M cross F to F to M was your projection map, and then you had a map from M to F. This whole pi Okay. What was a section, man? A section was M to E, which then happens to be like sigma pi is just ID, right? We just come to the same point. Then such a section is locally can be represented by this particular M to E map, the base M to F M cross F, base to fiber. You saw in specific product bundle case, you just need to generalize it. I will see the subtlety there. And then pullback of a bundle. We define so-called pullback of a bundle. Sections are also pullback. And then the important notion of classes and charts, atlas and charts. Very important notions. I mean, this enlighten you with the things I've been doing, ignorantly. So there's that. You define what the chart is, from an open set around a point in a manifold, homomorphism from there to an RD dimension of manifold and D equals dimension manifold. You see component functions, and then you set off all those charts. You get classes, and you define C0 atlases where your C0 compatible charts. You define C0 compatible charts, and you play around with chart maps now, right? They give you a beautiful way to translate your abstract manifolds to Euclidean spaces. You play around with chart maps. So you define C0 atlas. All those charts which are paired by C0 compatible are in A. No. C0 atlas is like, if you take any two charts in it, they are C0 compatible. Okay, cool, fair enough. Now, that means that you can go from one chart to other chart in a continuous fashion. So now you define so-called maximal atlas. Now if you find the different atlases, that's an issue. So you look for maximal atlases. C0 atlas, which is maximal. With respect to the C0 compatibility again, that's fine. Okay. Again, doing manifolds from Atlas point of view, you charts. Okay. I did this again because they were very important, and it is important to get the good idea of things now. Okay. The whole forgetting internal mechanics thing and going just chart to chart, Cartesian to coordinate without the idea of anything. And then mates, we have differential manifolds. All these atlases for this. You can define what a differential manifold is in terms of the classes that you take. So the important notion is that any topological manifold has only one maximal topological atlas, right? Because all the charts are C0 compatible in it, and if you just take all the charts, you get a maximal topological atlas. C0 atlas in a topological manifold, in a given topological manifold M and O. So then you say an atlas A is a so and so atlas if any two charts are so and so compatible. Now this so and so can be C0, Ck, K belongs to natural numbers, and say infinity, then you call a smooth compatible. Plus then C omega, real analytic manifolds. That can be Taylor expanded basically. Then complex transition functions satisfy the Cauchy-Riemann condition equations. That's a very strong. That's a very strong thinking in real numbers, but it's a weak condition in the sense that it gives only differentiability in complex space, or well. Okay. You have a theorem due to Whitney that any maximal Ck atlas contains a C infinity atlas. Now we have defined this so and so compatibility, and that compatibility is basically reflects the compatibility between the so and so compatibility of atlas is essentially reflected by the so and so compatibility of the charts. And how is that compatibility between charts is defined is through the transition functions between two chart maps. Between two charts. Between two between two Euclidean spaces. But the transition functions are what we are imposing upon these compatibility things, right? Ck, C0, C infinity, Cauchy-Riemann conditions, that is the complex compatibility and real analytic compatibility, C omega and stuff. So omega is a real number? I suppose so. The hell, or just a notion? Yeah, just a notation. And then you say this theorem due to Whitney that any maximal Ck atlas actually contains the C infinity atlas, and two maximum Ck atlases that contain the same C infinity atlases are already identical. Okay. We have two C infinity atlases. Okay. If you have two Ck atlases that contain same C infinity atlases, they are already identical. Okay. Now this is a very strong thing. You get C infinity atlases out of nowhere. One can probe this proof, right? Some so and so compatibility we have defined here, and then it just keeps crashing. So we have defined the so and so compatibility in this section, and then we are doing the Whitney theorem. In Whitney theorem, one could probe this, probe in the sense, look at its proof, look at its implications, and play around with it. And then we define so-called a Ck manifold or a so and so manifold. It's a triple M, O, and atlas A, where MO is a topological manifold, N is a maximal Ck atlas. It's a so and so atlas, right? It's a smooth manifold, Ck manifold, or whatever. A given topological manifold can carry different incompatible atlases. I would like to probe this. Okay, that's fine. Now, so what's the problem with this? That which atlas you take exactly? So which atlas you take? You have the notion of different compatibility. Now, is that not issue? Is that not an issue? Decision to choose a smooth structure problem. Now that will probe that issue. I mean, physicists will. Okay, that's what the dramatic. The statement is that the physicists will suffer from it. If you have different notions of differentiability in a given manifold, then it may be problematic to see for the dreams of physicists to look at everything and no, I don't know. Well, whatever. Then we see maps between CK manifolds or smooth manifolds. Yeah, CK manifolds. We call that map between CK manifolds smooth if you define it. I don't want to go through it actually. I mean, a chart in an atlas with and some chart in CK. So it's kind of the same thing again. You just go through the charts, the images of the charts in the Harden manifold. It's the map between them that should be contained. That should be CK. That's a simple notion. That's the simple notion of CK differentiability. I mean, that's the differentiability in a map from manifold to manifold, CK manifold to CK manifold. Okay, prove that this lifting of notion of differentiability from chart representation of phi to the manifold is well defined. Now, is this well defined? Everybody asks. This lifting of notion of differentiability from chart representation phi to manifold is well defined. Okay, can take different charts and probe the same thing. So, how do you do that? Well, you say you take different charts and you just say that different charts, that is, just take a different map from the same open set in manifold for simplicity. Then you go to into RD, and then you see all the continuous maps exist from there, and so what happens is you get a very nice map from So if you just restrict the atlas to CK, and then you just restricting atlas to CK, so the other maps are also CK, and this composition turns out to be CK, and it doesn't matter if you choose a different chart, right? The y composed phi composed x inverse CK implies that y tilde phi and x tilde inverse is CK. Of course, okay, yeah. And then, if this phi is bijective and its inverse is continuous, inverse is C infinity. If this phi map is bijective and phi inverse are C infinity, then phi is a diffeomorphism. It's called a diffeomorphism. There are the the structure preserving maps between differential manifolds. The differentiability structure, whatever we have given to the manifolds, this diffeomorphism preserves it. Say two manifolds are diffeomorphic or isomorphic with respect to differential structure. That's what this means. Now, there's a very, 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 very interesting things. In different dimensions, you see what differentiable manifolds you can get. What differential manifolds you can get. And you see that you can only get some and whatever that is. It's very interesting. We'll go to it, but you cannot not mention this dabba that he drew in between a lecture. It just clarified his intuition on the subject. Started from a set. He gave topology to the set, gave a blob product, the group structure to the set. He allowed that group structure to also, you allowed that set to have a group structure followed by some topology, calling it differential structure to the topology. You get a Lie group. This is interesting. Set with you give some set topology, and then you move on to giving it a differentiable structure leading to a differentiable manifolds and stuff, and then you give set its blob product, giving it a group structure, and then allowing that set to also have a topological structure, which simply gives out the differentiable structure also. You see, a Lie group, if you say that it's a Lie group, is a group which also has a manifold structure, right? Which is also a manifold. Now this ensures that it also has a differentiable structure to it. It is a differentiable manifold by nature. So it's a very important thing. Lie groups are differentiable. That the above is good. And then he said we can give some other structures and vector space structures and stuff. The Lie algebras and stuff. Okay. Now we have two different atlases. Are they diffeomorphic is the question. You see, in real line we saw two different atlases. That is two which are incompatible. Like if they are compatible, they'll be in the same atlas, so it doesn't matter. So they're incompatible, and we got two such things. Are they diffeomorphic? If they're diffeomorphic to our differentiability through our diffeomorphic glasses, it's just same. So the question now is, the play now is how many different differentiable manifolds differentiable structures can one put on a given topological manifolds up to diffeomorphisms. How many can you put? How many such structures can it be possible? Now that turns out to be depends on the dimension of manifold. Fair enough. And for dimensions 1, 2 and 3, there is a unique differentiable manifold one can make of a given topological manifold. Now this result is something interesting one can probe into. It's a Redon-Moise theorem. I'll definitely look it up, probe it. Okay, I just thought to review. I just thought to go through the names of the topics, and I'm actually quite discussing much, I guess. I don't know. CK manifolds, yeah. I need to try it also, right? So it helps. So CK manifolds, differentiable maps between manifolds, between CK manifolds, and then you have this notion of diffeomorphism, and now then the deep result comes. The deep results of if you take any manifold in dimensions 1, 2, 3, any differentiable manifold that is differing by classes that are diffeomorphic in nature, there's a unique differentiable manifold one can make for given topological manifold in dimensions 1, 2, 3. That is brilliant. Construct higher manifolds, higher dimensional manifolds, by doing so-called surgery and constructing the higher manifolds using some lower dimensional topological spaces, and and then you kind of look at how the homotopic groups or fundamental groups are going, and then you that's fair enough, that's interesting. Okay, so there's that interesting thing that if physicists say that we need a 10-dimensional manifold to explain reality, then you better deal with differential structures. But then you could argue that you can just do an experiment and see which differentiability makes sense and what. It's interesting. I see there's this notion of understanding something and understanding the language that you use to understand something. And mathematics is really that tool that you have to understand it pretty well. It's just interesting. You can create anything. Okay, anyway. So in-dimensional 4, trouble. Dim greater than 4, dim equals to 4, Okay. The live stream is still learning, so that's good. I mean, it breaks up, but nevertheless it's working fine. Dimension equals 4 is a trouble zone. Dimension equals to 4 first reminds us of space-time. It's in R3 1,3 time, and so what that deep puzzle says is, in a non-compact space, non-compact manifold, there are uncountably many differentiable smooth manifolds. Differential smooth manifold that can be constructed out of single given manifold, 4-dimensional manifold. Yep. Just take a 4 and R4 and you get uncountably many differential structures. Now constructing these differential structures and actually doing the math of it, this is what I guess occupies physics. I mean, I don't know, people do, of course, I guess people do it here. I mean, how can they possibly do structures? But then you see, what was a differential structure? It's just giving a maximal CK atlas, right? It's just a maximal CK atlas that you have, right? Right, that's the thing. So just a CK atlas, and now you need a CK maps. Now the moment you say CK maps and what maps can be constructed, you need to look at the function space of that and you have to see, I guess. I mean, that's an interesting thing to probe. So I could look at some sources on this, the proofs of it, how how do they do such stuff? And a compact space, there are partial results that the B2 Betty number 2 is, if it is greater than 18, you have a countably many. Countably many, basically infinite. Also infinitely and countably many structures that can be padded on a given manifold. So what about the R4 that we use in special relativity so much? Which true smooth structure are we going to take? So yeah, that is a problem. I don't know, is it related to Riemannian manifolds? You take Riemannian metric, you make a Riemannian differential structure to it. I mean, physical spaces are metrizable spaces, I suppose. I don't know. I mean, at least in classical theories, not quantum mechanics. Quantum mechanics is a whole different ball game. But yeah. Anyway, I don't know if I'm doing a good job. I mean, I'm just looking at results. I'm just understanding definitions. I'm looking at results. I'm interested to probe them. That's what I'm going to do in the next session. But you see, I'm still having fun. I mean, I am enjoying it. I mean, there should be no negative thoughts about it. It's just I'm enjoying it. What else? What do we need? Okay, whatever. Okay. So yeah. Fair enough. So in a compact space, there are partial results, and it puts special relativity in trouble. Okay, good. I like it. I like how math puts trouble on physics. I mean, it should. Come on, it should. Okay. So we have differentiable structures now. Differentiable structures, we have not vector spaces or what, and modules and whatever. Okay. But then we start looking at. I mean, there are some very subtle notions beginning from here, I suppose. Like we start looking at vector spaces in this lecture. This is lecture 8 at this point. Start looking at vector spaces where there are general, the general structures and the homomorphisms between vector spaces. There's some terminology, endomorphisms, basics, and then you define the homomorphisms between them, and then homomorphisms, and then the terminology, home, endo, automorphisms, the dual of vector spaces, and then these are good stuff. And I just don't believe how. I mean, you just play around with this. The theory comes next again. You define a tensor, then a PQ tensor, you call it PQ tensor. It's a multilinear map from V star or V cross V. At this point, the abstraction begins like, you just construct for the sake of construction. And but it seems like there is a brilliant piece of math coming up. Okay, because the next lecture is, remember, it's a tensor space theory too. You make use of these tensors and you construct something important. And I feel there are differential forms, and you take wedge products between them, and you define a measure. I don't like to use this word measure because I don't know it. That volume element, that integration parameter, or whatever that is. You can define integration. See, if we define a differentiable structure to construct some tangent spaces, we go to the tensor theory now. We construct homomorphisms between maps. We define tensors. We define tensor products. If you have two tensors, we also construct tensor product. And why is this useful? We'll see. And then there are very subtle aspects of what a 0-1 tangent. What is 0-1 tensor of this vector space V we are talking about? It just turns out it's a dual. You just see the definition, and just turns out it's a dual. It's a dual vector space of the given vector space. And then you take 1-1 vector. It's a V cross V star by notation, and it's a tensor from V star cross V to K. And the claim becomes now it's an endomorphism on V star. And what's an endomorphism on V star is a map from V star to itself, right? That's the endomorphism. It stays in itself, right? It's a homomorphism from V star to V star. That's very interesting because, this is interesting just for the sake of it. Okay, so you constructed a map. This T cross S is Then you look at why not T10V, is it a vector? Is it just isomorphic to vector space? And then these explicit. He also put this in a problem sheet, so that's that. There's that. I will do it. I'll probe this. It's going to be a long session. I love it. So you define now. You give some thing called a basis root. Now you give a basis root. See, now you define the so-called. Now you define a basis, right? You give a Hamel basis without any structure. Also, you give a basis root. Hamel basis. So, yep. When we classify vector spaces as infinite dimensional, finite dimensional, then decomposing things, vectors. How do you? Representing a vector in an abstract vector space as a summation over the basis with components and stuff. The components of tensor also you define. Define components of tensor, and then you define change of basis. Change of basis and such stuff. Then some polemics on symmetry of numbers. Two quotes that a man never chooses a basis unless he between the basis linear summation convention. So how do vectors and covectors change if the basis change? They also change by the same thing. At the same transformation, except they are related to the inverse of each other and stuff. Inverse, again, the symmetry concept. Inverse is a general concept. You just take a product and you give a fucking delta AB, and that's it. More on determinants now. determinants, again, very subtle aspects of these are very subtle aspects. So for an endomorphism, that is T11V, we have defined you got a so-called a matrix structure and you have a formula to compute determinants and stuff. But then we see that we define determinants in a way that it gets shady to define determinants in a T0 to V. The symmetry of numbers was that having a cube, having that matrix and stuff. That visually appealing stuff has to go away. That's what he says. Position vectors, matrices and stuff, these have to go away. So, by linear forms, you have a matrix again. Okay. Whatever, you define determinants in a very subtle way. N form, he defines an N form, and this is getting important from here, right? The multilinear algebra, in a vector space of dimension D, we define an N form from 0 to D. It's a T0NV vector omega that is totally antisymmetric. Again, same thing is here. Change of basis, concurrence of vector sentences, concurrence of vectors and tensors, and then you have this thing called vectors, tensors, change of basis. What? Change of basis, and basis. I just lost it. Determinants and polymorphic determinants, and N forms. Using N form, we define local determinants. Top forms. Top forms N equals to T, basically. Then the volume. See? Things are beginning, bro. Things have begun. The next lecture, you just define fucking differential form. Okay. This stuff is more of a see. These are more I don't know. If they are on these next stuff. That's what analysis I've done. I guess that's why I'm going to be. I'm imagining stuff, and I don't know. I'm fluent about it, but algebra. It's a lot of doing than saying. Of course, everything is doing. This is just a review. This is the review part of the review. Again, it's just the first section of it. So, it's very dependent on definitions, and things fall apart of that. If I find determinants as only on amounts and don't want them to be that's V1. So basically maps from V to V itself. So you can map to itself. It's basically the top form acting basis of the innate set, and then divided by the top form acting on the basis of the real, the beginning of the domain vector space V. Some volumes you make some basis, but then you just take any different basis and you just get the same thing. Two top forms, both non-vanishing, then they just differ by constants. What is an n form basically? That is a totally antisymmetric piezo and V tensor. Correct. But any combination as you just say that this antisymmetric what happens, just take some n vectors, n start, just take n vectors from them and then just give out computed thing a sign. What? Yeah. Because these are completely just a number. 0. So that's a thing. It's just a teaser and tensor for now. That's got nothing to do with anything. Okay? Densities, and then you get principal fiber bundles to define such artifacts. Now this is getting again very abstract from multilinear algebra, but I hope we'll get there. Okay, so I hope we'll get there, right? Just a second. Okay. Now, sorry for the noise. Sorry to me. I messed up with the thing. And forgot to apply mine. I forgot a thing and I yeah, I forgot to apply this. Boo. Okay, I'm back. And the interesting so yeah, I was discussing about the tangent vector space that we defined. Now the set of all such tangent vectors at a point is a tangent vector space, and this turns out to be a vector space with this pointwise defined addition and multiplication. That turns out to be vector space, and then an aside on algebras and derivations. An aside on algebras and derivations. Some the vector space against the product that is a bilinear map is called an algebra if you have a blob. So the blob, that's it. Just define a blob and that's an algebra, that's it. Don't impose anything. Continuous, non-continuous, inverse, nothing. Just define a blob. See infinity as an algebra. Station. Then you have Poisson bracket in classical mechanics as a derivation in the algebra of functions in space. Okay, the observables in chemical mechanics with derivation. You identify the derivation of the derivative with respect to time. That is interesting, right? Because derivative satisfies Leibniz rule. And then a new theorem comes that dimension of the vector space of tangent space is equals to the dimension of the manifold we were talking about. Now this is out of charts you have to kind of build into it. It's a good exercise to do, and then you identify a basis in TPM. Basis in TPM. And then turns out it is a basis, and that's a good thing. And okay, anyway, have a basis. The coordinates maps are smooth and then the component of the tangent vector. You have things. Charts change करोगे तो components कैसे बदलेंगे is another question that I have given in the problem sheet. And then folks, you have this concept where under change of basis, vectors transform linearly, trances transform linearly, but not the position, the coordinates. No. Position vector is not a vector. It's just an artificial concept that we will not choose any further. And then, folks, we have entered the last lecture, which have rather colorfully written. It's an interesting topic. It deals with embedding, immersions, cotangent spaces, gradients, and tangent bundles. Very interesting. The first thing, as I told before, we could have defined the tangent space in a very intuitive way of constructing the space around a point P. But where does this lie in? Then you say that this whole space is actually an embedding of some bigger space where this lies, and you construct a tangent space around it, and blah blah blah. So there is an extensive definition around it. Now we have defined an intrinsic definition of it, right? The tangent vectors, it takes the functions from manifold to real lines to a real number, and now see the equivalence between the tangent, the whatever, intrinsic and extrinsic. So, but before that, embedding, immersions, cotangent spaces, tangent bundles. Okay, we started with defining cotangent spaces, just the dual of the tangent vector space that we have. So we don't need to construct anything. We have a dual basis to it. We construct a dual basis to it, and that's very interesting. How do you get the dual basis? You get a very, very peculiar but good looking, familiar looking map, a linear map from C infinity M to the cotangent space. Why? Because this map, folks, is a map from F to DPF. You call it DPF. On this, DPM star is essentially acting on, but it's basically TPM star, right? TPM star. What is TPM star? It's a map from TPM to K, right? Or itself, no, K. TPM to K, yes. So TPM to R here, in fact, TPM to R here. So it takes off a TPM, stacks on that, and then that's very peculiar looking, but nevertheless it's a basis. It defines a basis on TPM star. I mean, you take the basis and you do some stuff, you get a basis on it. Basis on TPM co, you act on this DPF, it turns out that is also a basis on TPM star. Call this as a gradient operator. You even call it a derivative. Define a derivative soon somewhere. It has to be tangent to a level set. The tonality between the gradient. Okay. It's time that I take my trypsin dose and wait for an hour to do my lunch. So that's that. You have a cotangent space, you define a gradient operator, then that defines you a basis, a very good basis. It's just not any basis, it's a dual basis of the dual of TPM, that is the dual basis on F star M, basically the basis that generated by from the that we have used there in the start. And then we define a very good topic of push forward and pull back. Push forward and pull back. It's interesting how even complicated topics like these, Frederic just deals with them in a very intuitive manner. This push forward is a tangent space. It's a map from tangent space of M to tangent space of N. Given a map from pi M to N, the push forward is a map from TPM to TPN, which is defined in a certain way and stuff. It defines in a certain way, right? Yeah, it's defined in a certain way. That I'll get out, right? Now, this 5 star is also called a derivative of F at P. So the tangent vector of this is tangent vector of that. Vector of this is pushed to tangent vector of that, and it's in a very interesting way. It just pushes to this. A very specific tangent vector under 5 star. Okay, good. You have a tangent vector here. You also map to tangent to very specific tangent vector there. right? Interesting. By the way, the weather is beautiful around here. It's cloudy, it's windy, it's colorful. Good. I wish I could go out, but I cannot for a few days. So anyway, and then we define pullback. Okay, it's kind of a similar notion, but it starts from, this. And then and then we define it in a certain way too. Then the use of this is, the vectors are pushed forward, the covectors are pulled back. You can define only these maps. That's the thing. Now if a very special case of diffeomorphism between M and N, you can define both of them. Both can be pushed forward and both can pull back without both can push forward and push back. Now decide the question under which contours under smooth manifolds can we sit in some Rn. Now we start embedding. We define so-called immersion, embedding, and very important results that any manifold can be embedded in real. Embedding two times the dimension of itself, function of -1 and stuff. Embedding, definition of embedding, immersion, and then where it can be embedded. and then this clarifies the intrinsic extrinsic definition of tangent planes, which he did not deal with, or I have to probe it in a way I could do. So this is a probing point. Okay, and then we discuss the infamous tangent bundles and vector fields. This is where I was stuck because I had too much of stuff already. So they are just the disjoint union of all the tangent spaces you get at each point. You get a tangent space at a point, you get another point, you take the union of all of them, or at all tangent spaces at all points, they're disjoint, and define a projection map. At this point you just get a set bundle, but then you have you want to make it into. That's the question I did not answer. That's the question which I did not continue to get enlightened about. That I will continue after the whole stuff. Okay, so fair enough. That was a review of things. That was a review from lecture, 5 to 10. That was just a small review. I did not study them. I did not play around with them. Session 1 ends here. The review. Before the review. You look at it, right? You have an idea of how things happen, and to get an idea of what have you done. And you also learned you revised many things along the way, right? You see, towards the end I got tired, and also they were very fresh, so I had to look at them from an outside perspective. That's what I did there. It helps. Now I will go to the inside perspective after lunch. Okay? After lunch, because I shouldn't burn myself out of this, right? So session 2 begins post lunch. Session 2. Okay, question 2. We'll start after lunch, post lunch. I started at 11 stream, right? Yeah. Now it's 12:40, so it's 1 hour 40 minutes. Fair enough. Right, fair enough. So yeah. Okay, maybe an end song of first session.
These cold nights.
rises slowly as you walk away from all the fears and all the faults you've left behind. The harvest left no fruit for you to eat. You cannibal, you meat eater, you see. But I have seen the same, I know the shame in your defeat. But I will hold on hope, and I won't let you choke on the noose around your neck. And I'll find strength in pain, and I will change my ways. I'll know my name as it's cold again. So come out of your cave, walking on your hands, and see the world hanging upside down. You can understand dependence when you know the maker's land. So make your sirens call and sing all you want. I will not hear what you have to say, 'cause I need freedom now, and I need to know how to live my life as it's meant to be. heart.